Okay, so I asked you to find me these, right? Okay. Ah. My remote is driving me nuts. There we go. X plus 1 to the 0. Anything to the 0 is 1. Okay. Let's see. Someone from pod 1. X plus 1 to the first. Nice. Someone from pod 3. X plus 1 squared. You guys?
X squared plus 1.
Excellent. Someone from pod 5. X plus 1 the quantity cube.
X to the third plus 3x squared plus 3x plus 1.
Someone from pod 6. X plus 1 the quantity to the fourth.
X to the fourth plus 4x to the third plus 6x squared plus 4x plus 1.
Excellent. Observations. Okay, so the x is always to the first, the highest degree is always matches with the exponent, right? The number of terms, one more than the exponent.
The first term always has a 1.
Okay, the leading coefficient's always 1. What's true about the constant? 1. Okay, let's look at all these coefficients. 1, and then 1, 1, and then 1, 2, 1, and then 1, 3, 3, 1, 1, 4, 6, 4, 1. Anybody wants to guess what x plus 1 to the 5th is without multiplying it out? Okay, how you getting those numbers? Oh, that pyramid triangle thing. Pascal's triangle. These numbers that are right here, what are they compared to the last page? Those are all the coefficients, right? Yes. Okay. Well, let's talk about the pattern of Pascal's triangle. What would the next row be? 1, 6, 15. Okay. You take the 2 and add them together, right? Okay. So what is nice about multiplying a binomial is that it follows the pattern of Pascal's triangle. So this Pascal's triangle is going to give you the coefficients of x plus y raised to the n power. Pascal's triangle will describe the coefficients of expanding x plus y to the nth power. Okay. Now, if I gave you something raised to the 9th power, first of all, it is tedious for me to have you multiply a binomial 8 times, right? That's ridiculous. Okay, so we have the binomial theorem to help us have a shortcut. Now, if I ask you to multiply a binomial raised to the ninth power, am I really going to have you write Pascal's triangle out to the ninth row? Or really, it would be the 10th row. That would also be tedious, wouldn't it? Don't you think? Writing a triangle, adding all these numbers, okay, that's tedious. So instead what we can use is this. This is the binomial theorem. Write it down, we'll talk about it, and then we'll explain how this relates to anything we've been talking about with Pascal's triangle. Okay, so basically this describes every single term in your expansion. Okay? If you have a binomial raised to the 5th power, there's going to be 6 different terms in that. Okay? And so instead of multiplying something out that many times, we can describe each term. Okay, so what does this mean? So this means what? This means a sum. Okay. We're going to start at 0 and at n of all of this. So let's just, this is how it will look in general. Like, let's say, okay, so this matches this right here, which matches this right here. Okay. So whatever your power is raised to, that's going to be that first number in your combination. So if this is 10, this is 10 to something every single time. Okay? You're going to start your combination at 0. So 10 combinations of 0. And then your next term would have 10 combinations of 1. And then your next term would have 10 combinations of 2, etc., etc. Okay? This number right here will always match the exponent of that second term. Okay? And I don't really want to explain too much about this until we actually do an example. Okay? But we've been talking about Pascal's triangle. And I made you do all that work to find the pattern of Pascal's triangle. So why am I not talking about Pascal's triangle anymore? I really am. Pascal's triangle is the same as what was on the previous slide, okay? If we notice, if we use combinations, so like here in the 0 row, I have 0 combinations of 0. That's 1. Here in the first row, 1 combinations of 0, and then 1 combination of 1. Well, that's the same thing as 1. Okay, on down. Here down in, I call this the 4th row. I know it's really the 5th row, so I'm just going to go ahead and call this the 0 row. That way you're not confused, okay? So here in this 4th row, 4 combinations of 0, 4 combinations of 1, all the way to 4 combinations of 4. Those match the 1, 4, 6, 4, 1. Okay? So instead of having to write out Pascal's triangle every single time, which would be a waste of our time, we can just recognize that all of these are combinations. Okay? So get out your calculator and let's remember how to find that combination button. Right? Okay, so this is the formula for combinations. You're probably not going to use it. but it is in your calculator as math, under the math, and then probability. Okay. I also want to make note that this is also a notation for combination with the parentheses n stacked on top of r. So this is the same as n choose r. Okay. You may not deal with that a whole lot right now, but if you see it again, maybe in like in a statistics class or a combinatorics class, I want you to know what that means. Okay. So just to get our calculators warmed up, especially if they were left in your car over the weekend, please find me 8 combinations of 2. Just make sure your calculator works. You can use it correctly. What is it? Are you getting 28? Excellent. What does this mean?
10 choose 3.
10 choose 3. 10 combinations of 3. Michaela says 120. Yeah? All right, our calculators work. Excellent. So, let's use the binomial theorem. Now, since we've done this before, the example that I chose isn't just x plus y. Okay? Now, if you refer back to the binomial theorem when I had you write it down, right? It was the n combinations of r, x is raised to a power, y is raised to a power, okay? So in this case, our first term, or the x in that equation, is really 2x, and the second term is the minus 3, okay? So we're going to treat that as a negative 3, okay? So since this is written to the 4th power, we're going to have 4 combinations of, we begin with
0.
4 combinations of 0. Our first term is going to be raised to the 4th power. And our second term to the 0 power. You're always going to start like that. Where you have the 4 combinations of 0. Your first term is raised to that power. Your second term to the 0 power. Then we're going to move on. 4 combinations of 1. Your first term, you're going to decrease its power. Your second term, you're going to increase. Notice how this number right here, everyone look, this number always matches this power right here. Okay. Next term, 4 combinations of 2. 2x is now to the second power because we decrease, and negative 3 is now to the second power because we increase. Then we move to 4 combinations of 3. 2x is now to the first power, and negative 3 is to the third power. We decrease the first exponent every time, we increase the second exponent every time. And then 4 combinations of 4. We know we are on our last term. It's 4 combinations of 4. We have nowhere else to go after that. So then 2x is now to the 0 power, and negative 3 to the 4th. Okay? So now, help me out here. What is 4 combinations of 0? 1 times 2x to the 4th. 16x to the fourth. And what is negative 3 to the 0?
1.
Okay, so that means our first term is 16x to the fourth. Okay, let's move to our second term. 4 combinations of 1 times 2x, the quantity cubed. 8x cubed times negative 3 to the first.
3.
Negative 3. So what do we have? What's our second term? Negative 96 x cubed. Okay. Our third term, we start out with 4 combinations of 2. 6. 2x the quantity squared. 4x squared. And negative 3 squared. Positive 9. So our third term is a positive 216x squared. Okay. 4 combinations of 3. We're moving on to our fourth term. 4. 2x to the first. 2x. Negative 3 the quantity cubed.
Negative 27.
Negative 27. So our fourth term negative 216x. And then our last term, 4 combinations of 4 is 1. 2x to the 0 is 1. And negative 3 to the fourth would be
80.
what?
80.
Instead of having to do multiplication 3 times with our 4 binomials, we could just think about what each term would look like in that pattern.
So this would follow the triangle.
Hmm?
This wouldn't follow the triangle.
Well, it does. These right here, the 1, 4,
The
6,
coefficients.
4, 1. So those coefficients are following the triangle, but you have to take into consideration that 2x and that 3. Okay? That they're being raised to those powers. Any questions? How much did we really have to think?
Oh,
Okay? We had to set up each term, and then it was plugging into our calculator, right? This much. You guys are good at this one. Okay, let's look at another one. Ooh, x squared plus 4, the quantity cubed. Now this one wouldn't be terrible to multiply out by hand, but let's just look at what the binomial theorem does for us here. Okay. So help me out. Our first term starts out with what as the coefficient?
3.
How about in terms of a combination?
3.
3 combinations of 0. Thank you. Times. Okay, so our first term, cubed, times our second term to the 0. And since this is plus 4, I'm just going to make it, it's going to be a positive 4. Okay? We'll come back to that later. Our second term, what does it look like?
3. Three combinations of one.
3 combinations of 1. Our first term is being raised to the, and our second term to the first. These two numbers should always add up to your original exponent. Did these add up to 3? Yep, we're good to go. Next term, 3 combinations of 2. X squared to the
First.
4 to the, great. And last term, 3 combinations of 3, x squared to the 0, or cubed. Okay, so here we go. These should be nice calculations. 3 combinations of 0. Anything combinations of 0 is 1. X squared cubed. 4 to the 0. So our first term is x to the 6th. Okay. Second term, 3 combinations of 1. 3. Let me give you a little hint here. Anything combinations of 1. 3 combinations of 1. 4 combinations of 1. 5 combinations of 1. There's going to be a pattern, and what's that pattern going to be? That it'll be that number. 3 combinations of 1 is 3. Okay, x squared squared. 4 to the first. So what's our second term?
12x.
Great. 3 combinations of 2. 3. X squared to the first. 4 squared. So our next term is? You need a calculator. 40 what?
48.
Okay. And then our last term, 3 combinations of 3, x squared to the 0, and 4 cubed. What's 4 cubed? Thank you. You should know that off the top of your head. Yes, Kyler.
For the first and last term, do we need to write like the 3C040 because we know they're going to be 1, and I think the last one, like 3 choose 3, like that one calls going to be 1.
So, would you need to write it? Not necessarily.
Okay.
And if you write 3 here instead of 3 combination of 1, and that's what it is, that's fine. Okay. All right, so here we've done, okay, we have found the entire expansion. Okay, what's the point of the binomial theorem? Why do we do this? Why do we do this?
It's easier.
Easier than what?
Easier than the triangle and multiplying it out.
Okay, this is a shortcut for actually multiplying everything out. X squared plus 4 times x squared plus 4 times x squared plus 4. Okay, it's just a shortcut as opposed to multiplying out. Now, it still took us some work, yeah, but the chance of error is a little bit less in this, okay? Now, we also can use it to help us find a particular term, okay? So, here I have a plus 2b to the 8th, and I want the 6th term, okay? Now, we're not going to multiply 8 binomials together just to find one term, okay? That would be ridiculous. But we have a pattern for what each of these terms look like. So first, what I want you to notice, when we use the binomial theorem, we start out with that n choose 0, right? And that's our first term. And so then our second term is n choose 1. And our third term is n choose 2. Are you with me? So if we're gonna find our sixth term, okay, here's,
So would you do 8 choose?
well, we would do 8, choose what? We would do 8, choose 5. Because our first term is 8, choose 0. Our second term would be 8, choose 1. So our sixth term is really when we were putting that 5 in there. Okay? So let's remember what this looks like. So we're going to have a raised to a power and 2b raised to a power. Now, which exponent is going to be 5? 2b. Remember, those two numbers are always going to match. And if that exponent is 5, what does this need to be? 3, because those two need to add together to be the 8. Okay? So, I'll go ahead and let you do some calculator work here. Sarah, what'd you get for your term? What'd you get? Just 56 A cubed? Okay, so you have 56 A cubed times.
Oh, I told you that.
Okay. What did you get for 8 combinations of 5? Okay. And then we have A cubed, right? And then what did you get for 2B to the 5th?
32.
So 32 to the 5th, right? So what is 56 times 32?
1007.
That, right? A cubed B. That's what I was trying to get you to say. So you had that, you were just going. Okay. So that should be our 6th term. You agree? Okay. Now that for sure is way better than actually multiplying 8 binomials together, you know? Can you even imagine that? I mean, doesn't that just kind of make your stomach hurt a little bit thinking about all of that multiplication? Right? Yeah.
So this could have helped us for roller coaster projects,
Could have, yeah. But you knew it for your roller coaster project. Okay, one last example. Find the coefficient of the term a to the 6th, b to the 5th in this expansion. Ooh, write it down. Okay, so first of all, if it's a to the 6th, b to the 5th, then let's fill in what we know. All right, we're looking at one term, so we have 11 combinations of something, because this is 11. We have 3a to the something and negative 2b to the something. 3a needs to be to what power if I want a to the 6th? The 6th, okay? Negative 2b needs to be to what power if I want b to the 5th? The 5th, okay? So based on that, what should this number right here be? Because this number should match this exponent right here. Okay? All right, work some calculator magic here. It's really not magic, it's just calculation. Okay, you have 3 numbers to find and multiply together. you have an answer? What'd you get?
Negative.
Okay, thank God we didn't have to multiply that. Now, one thing. I love Courtney's answer, except for one thing. What don't I love about Courtney's answer? Tyler.
You don't need variables, you just turn the coefficient.
Okay, so all it asked for was the coefficient. So this would be the term. This is our coefficient. Didn't change the process at all. Excellent. Here is your homework. Okay, now I will tell you, this will be the last time I give you a book assignment this week, but you will need your book for final review. So don't think that you can just leave it behind after today. Okay, you might want to bring it for when we ask questions about this stuff tomorrow. But then the rest of the week will be review worksheets or an assessment of some sort. Okay. But next week you will still need your book for final review. Yay.